So we're starting Unit 2. Unit 2 is one of the bigger units in this book. There's a lot of material there. So it covers polynomial functions, rational functions, exponential and logarithmic functions. A lot of different types of functions. Chapter 3 is all about polynomial and rational functions. Chapter 4 is all about exponential and logarithmic functions. Okay. So I'm going to go ahead and get started with material. Chapter 3 starts out with complex numbers because we're going to need these when dealing with polynomial functions. Basically, when we have x squared is equal to a positive 36, that's going to produce two solutions. I'm going to solve x squared equals 36 by taking positive square root of 36, which gives me a 6. And I can also take a negative square root of 36, which gives me a negative 6. So negative 6 squared is equal to 36. Also 6 squared is equal to 36. But when I have an equation like x squared is equal to negative 36, there's no real numbers that I can square to give me a negative. So there's no real values that will satisfy x squared is equal to negative 36. And so we introduce this number, which we call an imaginary number. That number is always written as I. And we say that I is this non-real number such that I squared is equal to negative 1. A lot of times people think of I as the square root of negative 1. And that's a good way to use it as well. Okay. Technically, I is the non-real numbers that when we square it, we get negative 1. And that forces us to think of I as the square root of negative 1. Okay. Now, how we go from imaginary numbers to complex numbers is that we set up any complex number we can write as a plus bi, where I is that imaginary number I. And a and b are real numbers. So a complex number is anything that can be written as a plus bi, where a and b are real numbers. Now, the nice thing about complex numbers is that they form a field, just like real numbers. When you multiply complex numbers, you get back complex numbers. You multiply real numbers together, you get back real numbers. When you add complex numbers, you get back complex numbers. And when I say add, multiply, what you should realize is that in terms of complex numbers, if we set this value of b to be 0, then we get a plus 0 times I, which is a, and we get the real numbers, okay? So the real numbers are a subset of the complex numbers. So every real number we were looking at so far in the first couple of chapters is also a complex number. By the way, just as linguistic things, if A is equal to 0, then we get BI, and any number which we can write as BI, where B is not equal to 0, is called an imaginary number. All right? So I is the imaginary number where we square it to get -1. But any coefficient times I is also called an imaginary number. Like 3i is also imaginary. So if you hear me reference imaginary numbers, that's just coefficient times I. Complex numbers are any numbers of this form. So you can see imaginary numbers are a subset of complex numbers. Real numbers are a subset of complex numbers. So complex numbers are bigger than the real numbers in one sense of the word bigger. In the counting sense, it turns out they're the same size, but the complex numbers contain the real numbers, and the complex numbers contain the imaginary numbers. And any combination, A plus BI. Okay. So once we deal with the complex numbers, we want to do our basic operations on them. And that means we're going to add, subtract, multiply, divide. Whenever we do operations on complex numbers, basically we treat it kind of like we treated a polynomial. Add, subtract, multiply, divide a polynomial with variable I. But we have this added step where we know since I is imaginary, I squared is -1. That way, any higher power of I can be simplified to either a lower power of I or a real number. Does that make sense? And that's the nice thing about complex numbers. We don't need these higher powers of I. Because if we wanted to do I squared, we could say, oh yeah, that's -1 by definition. I to the third is like I squared times I. That's -1 times I, which is -I. I to the fourth, that's I squared times I squared. That's -1 times -1. So that's a +1. And that means anytime I have an I to the fourth, I can factor that out, call it 1, get to a smaller number or smaller exponent on my I. And so this pattern keeps going. I to the fifth is like factoring out an I to the fourth and then multiplying by I. So you just get 1 times I or I. I to the sixth is going to be factor out I to the fourth and you get I squared. So you get the same thing as I squared. I to the seventh is going to be the same thing as I to the third. I to the eighth is going to be the same thing as I to the fourth. And it goes in this pattern every fourth power. I, -1, -I, 1. And then I to the 13 would be I to the 14 would be -1, I to the 15 would be I to the 16 would be +1. So it's this pattern of powers of I, where we just go I, -1, I, 1. And that's because of the nature of the definition of imaginary number I. So we don't need those higher powers. We can simplify everything. After I add, subtract, multiply, and divide complex numbers, I can simplify it into another complex number. And that's what we're going to do. So let's take some examples. Here we have 2 plus 4i. And we're going to add 9 minus 3i. Then we have 6 minus 7i. Minus 2 minus 9i. 2 minus 9i is in parentheses. And then negative 3.5 plus 4.9i. Subtract the quantity 8.2 plus 7.7i. Again, we're just treating this like a polynomial. So we combine like terms. The like terms are the terms with the i's, and then the terms that are constants. So 2 and 9 combined to give me 11. 4i minus 3i gives me 1i. I can just put that as plus I if I want. Obviously, coefficients not written means coefficient is 1. In this scenario, all I have to do is remember to distribute that minus sign. Again, I might do that in my head if I were pressed for time, but if we're writing notes, I'll probably do it and write it down. So 6 minus 7i minus 2 plus 9i is what we have after I distribute that minus sign into both. And now I can combine the like terms of 6 and negative 2 and negative 7i and 9i. So that gives me 4 plus 2i. Same exact process for this one over here on the right. We have negative 3.5 plus 4.9i minus 8.2 minus 7.7i. So we just need to combine like terms again. We end up getting negative 11.7 and then minus 2.8i, I believe. Doing that in my head, so hopefully not right, but. So adding and subtracting complex numbers is just like adding and subtracting binomials, essentially. We're looking for like terms with the i's, like terms with the constants, and then when you subtract, you distribute on a negative sign. Now, the next operation is multiplication. It's a little bit more involved, and we'll see why that is. So here we have 3 examples. 6 times 2 plus 4i. And then I have 3 minus 7i multiplied times 1 minus 4i. And then negative 6 plus 9i. Multiplied times 5 minus 7i. So like I said, this is a little bit, will be more involved. If I'm doing this first problem, 6 times 2 is 12. 6 times 4i is going to be 24i. So it works again just like polynomials. We take number times coefficient. And this is it. This is the final answer. 12 plus 24i is your final answer for that problem. For this problem, we would just multiply as if we're multiplying binomials. 3 times 1 is 3. 3 times minus 4i is minus 12i. And then I multiply negative 7i times 1. And then negative 7i times a negative 4i. Now, for right now, I'm going to call that a positive 28i squared. So negative 7 times negative 4 gives me a positive 28. I times I is I squared. And here's where we have to do that simplification of higher powers of I. I have an I squared, so I'm going to turn that into a negative 1. Now, I'm going to write this intermediate step. I squared is negative 1. Which is basically telling me that that last term of 28i squared is essentially a negative 28. And then I can combine like terms. Now I could have combined these like terms right here in the first step too. Doesn't, sort of the order is not that important. But so now combine like terms. 3 and minus 28 give me a negative 25. Negative 12i minus 7i is minus 19i. So again, we multiplied the two complex numbers and we got out a complex number. So multiply two complex numbers, simplifies to a complex number. When we added two complex numbers, subtracted two complex numbers, we got out a complex number. I want you to try this one on your own. Come up with a complex number. You don't have to write every step that I wrote here, but I'll probably at least write those two steps, the first and the third. Negative 6 plus 9i times 5 minus 7i. All right, so let's go through this. Negative 6 times 5 is negative 30. Negative 6 times negative 7i, it's going to be a positive 42i. 9i times 5 is going to be a positive 45i. And then 9i times negative 7i, I'm going to start out writing that as negative 63 times I squared. And we've seen that the I squared is a negative 1 from the previous example. So I'm going to rewrite that as negative 1 times negative 63 in my head and just call that a positive 63. Now I can combine like terms. By the way, I'm doing it this way. Some people would combine the like terms and rewrite it immediately. Some people would skip that step and do that all in their head too. But 33 plus 87i is my final answer there. Everybody get that? $33 plus 87. So now we can add, subtract, and multiply complex numbers. In order to divide complex numbers, we need to use the concept of the complex conjugate. If I have a complex number, a plus bi, the complex conjugate of a plus bi is simply a minus bi. So the complex conjugate is just the complex number, but changing the sign on the imaginary part. If I haven't said this before, when you have a complex number, the A is called the real part, and the B is called the imaginary part, because that is, if you erase the other part, you get a real number, that's A. Erase the other part, you get an imaginary part, that's BI. So the A is the real part, the BI is the imaginary part. So we just change the sign on the imaginary part. And that gives us the complex conjugate. So if we want to find the complex conjugates of 1 plus 2i, or 2 minus 5i, or 3i, it's pretty straightforward. The complex conjugate of 1 plus 2i is 1 minus 2i. The complex conjugate of 2 minus 5i would be a 2 plus 5i. And the complex conjugate of 3i, that's like 0 plus 3i, would be negative 3i. Now, I want to do a little bit more than just find the complex conjugates. I want to show you why complex conjugates are useful. And I'll use these. That should say, and multiply. So think about taking 1 plus 2i times its complex conjugate of 1 minus 2i. Okay. So we know, we just said complex conjugate of 1 plus 2i is 1 minus 2i. If I take 1 times 1, I get 1. 1 times negative 2i is a minus 2i. 2i times 1 is a plus 2i. And then 2i times negative 2i is minus 4i squared. We can see what's going to happen. The middle two terms are going to go away. I'll write this in the next step. And because we're dealing with an I squared there, that turns into the real number of positive 4. And so altogether, the number times its complex conjugate is just 5. The real number 5. Let's take the other example, 2 minus 5i. We just said that the complex conjugate is 2 plus 5i. If I multiply the number times its complex conjugate, 2 times 2 is 4. 2 times 5i is 10i. Negative 5i times 2 is a minus 10i. And negative 5i times positive 5i is going to be a negative 25i squared. So we get 4 plus 10i minus 10i plus 25. Which gives us the real number 29. Now, this is going to happen no matter what our numbers are. If I have a plus bi, and I multiply times the complex conjugate, a minus bi, I'm going to get a squared. A times negative bi is minus a bi. Here we got a times bi again, that's positive a bi. And then we have b times negative b, so negative b squared times I squared. You can see that these middle terms are always going to drop out. And you'll always be left with a squared. This I squared turns into a negative, so you end up getting a negative of a negative. So you always get a squared plus b squared, which is a real number. And by the way, notice that we're taking a real number, squaring it, and then adding another real number, squaring it. So not only is it going to be a real number, it's going to be a positive real number. We're not going to get 0 unless both a and b are 0. And that's very useful. This process of doing complex conjugate multiplication is really useful when dividing complex numbers. Complex conjugates. Now we can divide complex numbers. Now I'm going to start out taking 6 minus 8i and dividing it by 2. And then I will start dividing by actual complex numbers that are not also real numbers. So I'll take 2 plus 9i, divide by 1 plus 2i. 3 plus 7i divided by 2 minus 5i. Notice that my denominators are exactly the things I saw the complex conjugates of a moment ago. 1 plus 2i, 2 minus 5i, 3i. Okay. So here's the trick. If we're dividing by a real number, this is a standard division problem. If I said take 6 minus 8x and divide it by 2, you would have just divided both the 6 and the 8 by 2, hopefully. You would have done 6 over 2 minus 8i over 2. And that's 3 minus 4i. So it's very easy to divide if our denominator is a real number. We just divide the coefficients. And so that's what we're going to do in these problems. We're going to force our denominator to be a real number. And the way we do that is we multiply this fraction by the number 1, and the number 1 is going to be in the form 1 minus 2i divided by 1 minus 2i. That way, when I expand out the denominator, I get a real number as my denominator, my new denominator. Now, I'll go through the multiplication in this case. Obviously, we just did this multiplication on the board in the denominator, but I'll still go through it. You'll also need to multiply the numerators as well. So for the numerators, 2 times 1 is 2. 2 times negative 2i is minus 4i. 9i times 1 is 9i. 9i times negative 2i is minus 18i squared. And then the denominator, 1 times 1, 1 times minus 2i, 2i times 1, and then 2i times negative 2i gives me negative 4i squared. I'm going to try to do this all in one step with the combining like terms and changing I squared to a negative 1. So I'm going to do combining like terms. This is going to be a 2 plus 18. So that gives me a 20. And this will give me a 5i. So we get 20 plus 5i. In the denominator, I'll do the same. I'll combine like terms. This one's nice because the middle two are just canceling out. This is 1 plus 4, just like we saw earlier, which is 5. And so this means that when we divided these two complex numbers, we end up with the complex number 4 plus 1i, or just 4 plus I. I take 20 divided by 5, 5i divided by 5, and I'm done. Okay with that? So I multiplied by a 1, which was complex conjugate over complex conjugate. That is complex conjugate of the denominator. That way, I ended up with a real number in my denominator. And then I could take this first piece divided by a real number, second piece divided by a real number. And that gives me my end result. So utilizing the complex conjugates shows us that when we take a complex number divided by a complex number, it's going to give us a complex number. I want you to try this one on your own. 3 plus 7i divided by 2 minus 5i. And if you want, you can do the 5 minus 7i as well, divided by 3i. I'm going to show you 2 different ways to do that, but you do that other one as well. 5 minus 7i divided by 3i. Please. Yeah. Okay. Sorry, I haven't done all the calculations. All right, so let me go through this. Again, our goal is to get the real number in the denominator and then use that. And the way we do that is we multiply the complex conjugate of the denominator on top and bottom of the fraction. So we multiply by 1, and the form of 1 that we're multiplying is 2 plus 5i divided by 2 plus 5i. 3 times 2 is 6. 3 times 5i is 15i. 7i times 2 is 7i. No, I'm sorry. 14i. 7i times 2, 14i. And then 7i times 5i is a positive 35 times I squared, which is going to be a negative 35 when I square the I. In the denominator, I get 4. We've already gone through this, but plus 10i minus 10i minus 25i squared. Again, that's going to be a positive 25 when I square that I. So combining like terms, after I square the I, this is going to be 6 minus 35. That's negative 29. Plus 15 plus 14, that's positive 29i. And then the denominator is 4 plus 25, that's 29. And then the middle terms cancel out. Now I'm ready to divide by this real number. Negative 29 divided by 29 is negative 1. 29 over 29 is 1. So we get negative 1 plus 1i as my final answer. Now, in terms of this last problem, there's actually a lot of different options on how you can accomplish this last problem. Okay. I'll show you 3 common options. Is that right? So, if we divide by 3i, divide by the imaginary number 3i. Option 1 is to use the complex conjugate, just like we've done over here. The complex conjugate of 3i, as we said earlier, is a negative 3i. So I multiply by the fraction negative 3i divided by negative 3i. So I get negative 15i plus 21i squared divided by negative 9i squared. So that's negative 15i minus 21 divided by a positive 9. And then we can do negative 15 over 9 is negative 5/3 I. Negative 21 over 9 is a negative 7 over 3 when I simplify it. Okay, 21 over 9. Both of them have a common factor of 3, so factor out 3. All right. By the way, obviously these have fractions as our constants and our coefficient of the I. When you do this, I know the 2 I gave you worked out where we had integers there. That's not always going to happen. Okay, sometimes you're going to get ugly looking fractions for these numbers, just like we did over there. So this is option 1, using the complex conjugate. Notice though that because we ended up multiplying by 3 i's and negative 3 i's and all that kind of stuff, what happened here was that we multiplied by 3i, and then eventually we had to do 15 over 9, and they both had factors of 3. Or 21 over 9, and they both had factors of 3. The goal of complex conjugate was just to get a real number in the denominator. It turns out when I have an imaginary denominator, we could simply use the imaginary number I and multiply that on top and bottom if I wanted to. And then I'd have a real number in the denominator. So if let me rephrase this, go to option 2, I'll say multiply by I, meaning take 5 minus 7i divided by 3i, and then multiply by I over I. What's going to happen is we're going to get 5i minus 7 times I squared. 5 times I is 5i. Negative 7 times I is going to give me a positive 7. Everybody okay with me doing that? I squared is negative 1. So negative 7 times negative 1 is positive 7. And then same thing here, 3i times I. 3 times I squared is going to give me a negative 1 times 3, which gives me a negative 3. So if I just multiply by I over I instead of by the complex conjugate, I also get a real number in the denominator. And sometimes this is easier to deal with because I don't have to simplify 15 over 9 or 21 over 9. Okay, so that's another option. Now the last option that I'm going to use, I'll call this option 3, is just divide by imaginary number I. This is a single term in the denominator. So what I can do is I can take 5 minus 7i over 3i and rewrite that as 5 divided by 3i minus 7i over 3i. And what you should know is that when I have a real number, 5 divided by 3i, dividing by I is like multiplying by a negative I. All right, I'll write that down. Dividing by I is like multiplying by I. So dividing by I, we have 5 divided by 3i. Dividing by this I would be just like multiplying 5/3 times a negative I. So I get negative 5/3. Now in this case, I don't have to worry about that because this I on top will cancel this I on bottom. I divided by I cancels out, gives me a 1. And I just get negative 7/3. I know why dividing by I is like multiplying by a negative I. It actually goes back to the powers of I thing. Okay. Remember that we said I to the first power is I squared is -1, I to the third is -I to the fourth is 1. Well, it works backwards too. But let me just state this. What if I did I to the third divided by I to the fourth? Well, one sense of that would say 3 factors of I cancel out with 3 factors of I. And you get 1 over I. Right? But what is I to the third? We just said I to the third is -I divided by I to the fourth, which is just 1. So dividing by I has to be the same as multiplying by a -I. That's one way to see it. The other way to see it is take this pattern and go backwards. Start I to the 0th power. Well, that has to match up with I to the fourth. The 0 has to be 1. And then if I go back 1, that's I to the -1 power. That has to be -I. And hopefully everybody knows that a -1 power is like dividing by I, right? Rules of exponent. Negative powers are like divided by that thing. So dividing by I is the same thing as multiplying by -I. And if you know that, then you can divide any imaginary number, divide by any imaginary number very quickly. These 2 options, options 2 and 3, were the quicker of the 2 options. A little bit quicker than complex conjugates, but now you have options of what you'd like to do. If you prefer, if you have this problem, you can multiply top and bottom by I. If that's good, you can multiply top and bottom by complex conjugates. Or you can divide by I, and now dividing by I is like multiplying by -I. Now, that is just for when we have an imaginary number in our denominator. Obviously, if we're doing stuff like this, I'm forced to use complex conjugates. I can't break this up. I'm forced to use complex conjugates if I have complex numbers that are not just real numbers or imaginary numbers. So if my complex number has a real part and an imaginary part, then I'm forced to use complex conjugates. But in the situation where my denominator is just a real number, I can do straight division. In the situation where my denominator is an imaginary number, I can also do, well, a couple of those options. All right. That was a little bit, probably longer than it needed to be, but thorough nonetheless. So now we know how to add, subtract, multiply, and divide complex numbers. Now what we're going to deal with is expressions involving square roots of negatives. And so what we're going to do is we're going to convert to complex numbers and then do the operations. Now, the one thing you have to be careful of when we're dealing with complex numbers and converting to complex numbers is that if I take the square root of a negative times the square root of a negative, I have to take out the I before doing the other operations. We'll see. I'll show you what I mean by that in a couple of examples from now. But basically, we want to convert to a complex number and then do the operations, knowing that square root of -1 can be replaced with I. So we'll take an example here where we have to simplify and compute. We have 5 minus the square root of -36 plus the quantity 6 plus the square root of -81. And then for our other problem, it says 10 minus the square root of -49 plus the square root of 64 plus the negative square root, or excuse me, plus the square root of -16. Okay. Now we're going to use a rule when I do this thing. And the rule is right over here. If I take the square root of A times B, I can do them individually as the square root of A times the square root of B. Right? It turns out that that's a rule as long as either A or B is positive. Okay. And without loss of generality, we'll just assume B is positive. So long as one of these is positive. Let's just say B is positive. Technically, it could be 0 as well. Sorry. But think positive. I'll be more technical. 0 works too. So as long as I don't have 2 negative numbers, then that rule works. Therefore, when I see something like -36, I'm going to, in my head, think this is like the square root of -1 times the square root of 36. And when I see something like the square root of -81, I'm going to think that's like the square root of -1 times the square root of 81. Usually I don't write that because we should all know that the square root of a negative number, -1, is I. So I just in my head think square root of a negative, that's I, square root of 36, that's 6. So this is going to be 5 minus I times 6 or 6 times I, doesn't matter what order you put those in. I'll put it in as 6I, because that's the way we're used to seeing it. And then over here, this is 6 plus I times 9, or 9 times I. So the square root of -1 becomes the I. And now I'm back where I started with complex numbers. Combine like terms. 11 minus 3I is my final answer. When I do this next problem, I won't write down this step. This is the one I'm just thinking through. What I'll just say, this is like 10 minus square root of 49 is 7, square root of negative is I, so that's 10 minus 7I. Yeah.
Wouldn't the answer to the first one be 11 plus 3I?
Plus, yeah, I misspoke. Better, let's write that. Yep, I did. Good. Good catch. Good catch. Should be a plus 3I. Yeah, to answer that first one, 11 plus 3I. I miswrote it on there. Minus 6 plus 9, positive 3. Yeah, good catch. So the second one, 10 minus 7I. Square root of 64 is just 8. That's the positive square root, so positive 8. And then plus, square root of negative is going to give me an I. Square root of 16 is 4. So I get 4I. And now I can combine. Just like we did earlier. This is going to be 18. And this one is going to be minus 3I. 18 minus 3I. And again, this is just the simplification rule that we're using. Square root of negative 36, square root of -1, square root of 36. Now, when you multiply two square roots together, something like square root of negative 25 times square root of 9, or square root of negative 45 times square root of negative 5. Square root of negative 15 times square root of negative 30. This is where I have to pay close attention to that taking out the I before doing other operations. Okay. So this is the scenario where I have to pay close attention to that. And I'll explain why as I go through these problems. So this one doesn't have any issues. Really. there's lots of options to go through this. What I would do is I'd probably take out the I, I'd call this 5i multiplied times 3, because we know the square root of 25 is 5, we know the square root of 9 is 3. So that's just 5i times 3, which is 15i. Now, somebody else may have went along and said, actually, what I would like to do is I'd like to use this rule. 9 is positive, so I could use this rule going backwards of the way we've been using it. And say negative 25 times 9 is negative, oh, now I get to think of that, 25 times 9, 225, is that right?
Yeah.
Yeah. So I could use the rule backwards and went negative 225 underneath my square root. Square root of negative is an I. Square root of 225 is also 15. So you could have done it that way as well. Both ways are good to go. In this example, the square root of 45 is not a nice number. Well, not nice decimal value anyways. The square root of 5 is not a nice decimal value. So in this one, what we would have to do is I would take out the I of both of these first. Square root of negative is an I, and then just leave the square root of 45 alone for now. Square root of negative is another I, and just leave the 5 alone for now. I times I is I squared. Square root of 45 times square root of 5 can be combined. 45 times 5 is once again 225. So I get I squared times the square root of 225. I squared is negative 1. Square root of 225 we just saw is 15. So we end up with a negative 15. So I pull the i's out, and then I use this rule in reverse. Okay. So I pulled the i's out, and then I use the rule in reverse. Now, here's why I say to be careful. Some people will mistakenly multiply negative 45 times negative 5. Inside a square root, but in this case, we get a positive 225 underneath the square root, and that would give us a positive 15. So notice that that is different than the answer that we got. This is not equal to our original expression. And it's not equal to our original expression precisely because we needed one of those things to be positive. So I follow that. For that rule to work, for me to be able to take square root of two numbers, multiply them, I need one, at least one of those numbers to be positive. So this is not the same thing as square root of negative 45 times square root of negative 5. Those are not the same. So that's why I'm emphasizing pull the i's out before you do the multiplication. Now, if we did the same thing here, we're going to get I times square root of 15 times I times square root of 30. That's going to be I squared times the square root of 15 times 30. And that's 450. 450 does not have a nice square root. But 450 is 225 times 2. Using the same square all the time here. Obvious reasons. So I can take the square root of 225, that's 15. That'll give me a negative 15. But then I have a square root of 2. That's left over. And I can't get rid of that square root of 2. It's just what it is. Does that make sense? Square root of 2 is irrational, so there's no way I can rewrite that. Okay. I don't think we'll go through these two, but I will mention what's happening in this case. Notice that all of the square roots are either positive or negative numbers of perfect squares. The ones that I'll give you, most of them will be perfect squares, so you'll be able to take a square root of them. You won't be left with a square root of 2 left over like we did in our last example. But you essentially convert these to complex numbers and then multiply just exactly the way we did before. Okay. Again, I don't think we need to do that. We've done enough multiplication of complex numbers that it'd be good to go. Any questions about how the operations of complex numbers go? Pretty straightforward. Well, that's the end of section 3.1. I'm going to start section 3.2 on quadratic functions right now. Let's just go ahead and answer. And like I said, this is the main part of chapter 3. We need to know what complex numbers are. We needed to know what complex numbers are, because sometimes we're going to get answers that are complex numbers. But the main push in chapter 3 is on quadratic and polynomial functions. Quadratic functions are one form of polynomial function. See that later. So a quadratic function can be written as f of x is equal to ax squared plus bx plus c, where a, b, and c are numbers. They're constants. We call that a quadratic equation in 2 variables when I can write y equals ax squared plus bx plus c. Now, this is what our book calls the general form. Okay. There are other books which will call that the standard form, but our book calls this the general form. Another way to write a quadratic function or a quadratic equation in two variables is in what our book calls the standard form. Other books might call this the vertex form. And that is f of x is equal to a times the quantity x minus h squared plus k. Or y equals a times the quantity x minus h squared plus k. This form should remind you of transformations. Remember we had our base function, f of x equals x squared. That's our base quadratic function. This is just that base function moved h units, either left or right, depending on whether h is positive or negative, and k units up or down, depending on whether k is positive or negative. And then the a can do things like stretch it vertically, shrink it vertically, or if a is negative, it flips it across the x-axis. So this is basically our base quadratic function transformed, shifted, and stretched in various ways. Stretched vertically by a factor of a, shifted h units in the x direction, k units in the y direction. This is often called vertex form because it turns out the hk is going to give you the vertex of the parabola, the graph that you draw. So there we go. With that standard form, or what our book calls the standard form, which I more likely call the vertex form. I'll try to use the book's terminology though too. We can see that it's obviously a transformation of f of x is equal to x squared. But even in the general form, this is also a transformation of f of x is equal to x squared. You may say, well, isn't there a middle term here? Yeah, that middle term does do something, but you can complete the square and transform any equation that looks like that into one that looks like that, or vice versa. Okay with that? So these are all transformations of f of x is equal to x squared. Okay. And a couple of things about the graph. Let's start with our standard form, or our vertex form. This is what I was just talking through earlier. If a is positive, then the parabola is going to point up. If a is negative, then the parabola is going to point down. We're going to be shifted in the x direction by h units. We're going to be shifted in the y direction by k units. So shifted horizontally by h units, vertically by k units. So those are big things to know. If a is positive, then it's pointing up. You guys know what I mean by pointing up, pointing down. When the parabola is doing this, when it's shooting off towards positive infinity, then I say we're pointing up there. And when the parabola is shooting off towards negative infinity, then we're pointing down in that case. So that's what we mean by up and down. Okay, it's where the arrows are going as x grows forever. And then shifted vertically. Now let's think of this in terms of a graph. In fact, let me, instead of, oh, that's why, okay. Instead of just talking through it, let's actually go to Desmos and graph a parabola in my standard form. I'll put an a value of 1 in front for right now. Okay. I want you to notice that as h gets shifted, it's just shifting left and right. Okay. The parabola is shifting left and right. As k gets shifted, the parabola is just moving up and down. Okay. But you'll notice, let's say I take a k of 3.5 and an h of -4, let's just say. Okay. What's the minimum value on that graph, the minimum y value? Well, the minimum y value happens right here. This is the point called the vertex. If the parabola is pointing up, like ours is, then the minimum value is going to happen at the vertex. There is no maximum value if the parabola is pointing up, because it goes off to infinity. Now, if you put a negative in front, if you flip it over, in other words, so flip across the x-axis and then shift. Then what happens is that your vertex becomes a maximum value, and there is no minimum value because the parabola shoots down towards negative infinity. So wherever we're shifting this, my vertex, specifically the y value of the vertex, is giving my minimum value of the graph. By the way, if you scroll out enough, you'll notice that you can go forever to the left, forever to the right. So the domain is going to be all real numbers, while the range is either going to be from the y value of your vertex to positive infinity, or from negative infinity up to the y value of your vertex. And notice that if the parabola is pointing down, that vertex gives you an absolute maximum. If the parabola was pointing up, the vertex would give you an absolute minimum. And that's essentially what that slide said earlier. It has a maximum or minimum point, That's at the vertex. We'll define that later. The domain is all real numbers. The range is either going to go from the maximum value down to negative infinity if the parabola is pointing down, or it's going to go from a minimum value up to positive infinity if the parabola is pointing up. Okay. So essentially, y value of the vertex to positive infinity, or the y value of the vertex down to negative infinity. Okay. Now, aside from the vertex, which is going to be at this minimum point or this maximum point, another feature of a parabola is that it has an axis of symmetry. An axis of symmetry is just a vertical line running through the vertex. And we say it's an axis of symmetry because the parabola is going to be symmetric about that line. You flip it and it looks like a mirror image of each. Both sides look like mirror images of each other. So if you flipped it over the axis of symmetry, it'd give you the same graph. So in this case, it's always going to be, well, in this case, it would be at -4. But in general, if you change this h to any value, that axis of symmetry is just going to be the h value. That works whether our parabola points up or down. So it's essentially happening at the x value of the vertex. X equals whatever number. That is our axis of symmetry. This vertical line where our parabola is symmetric. So any point over here has the same height as the point over there. And here's the deal. If we have our standard form, y equals, in parentheses, x minus h, quantities, I misspoke. Y equals a times, in parentheses, x minus h squared plus k. Then the vertex is at hk, just because of the nature of transformations of the parabola. So it's at hk. The axis of symmetry is going to be the vertical line, so it's going to be x equals a number, and that number happens to be the h. So if we have standard form, then our vertex is really easy to pick out, and our axis of symmetry is really easy to pick out. That's why sometimes this form is called the vertex form of quadratic, because you can pick out the vertex really quickly. Again, our book calls this the standard form, but other people call it the vertex form. So let's say we're given the vertex form of a quadratic equation or a quadratic function. We'll find the vertex and axis of symmetry of these quadratic equations, functions, and we'll give the minimum or maximum value. So you can see these two quadratic functions slash quadratic equations. So let's go through some of the features, maybe even before we write the vertex. The first thing I want you to notice is that in this equation, 2 is positive. So this parabola is going to be pointing up. Now the vertex for this parabola, we can just read off. Be careful, it's always x minus h. So the h in this case is a positive 3. And then it's always plus k. Again, be careful, that means that k is a negative 7. So it's x minus h squared and then plus k. So be careful about that. Since the vertex goes through the point 3, negative 7, or it is the point 3, negative 7, we know the axis of symmetry is x equals 3. Now, because our parabola points up, this equation is going to have a minimum value, but no maximum value. It goes off forever. And the minimum value of y is negative 7. And that happens when x is equal to 3, right? So the minimum y value is negative 7, happens when x is equal to 3. Other times people might say we have a minimum point at 3, negative 7. So that's another way to phrase that. And point is 3, negative 7. And then there is no maximum value because it shoots off to infinity. We can do a very similar thing over here. This is a parabola that's pointing down. That tells us something about where our vertex is going to be and what it's going to be. Vertex is nice to pick out. This is already in that vertex form. Be careful, remember it's always x minus h. So if I have an x plus 5, that's minus a negative 5. So the vertex has x value at negative 5 and y value of negative 3. This negative out front does not change the vertex, size hk, regardless of what number out front it is. We have the axis of symmetry. that is going to be x is equal to -5. And because this parabola points down, we're going to have a maximum value of y equal to -3 when x is equal to -5. So the maximum value is -3. The maximum output value, -3. And that happens when the input is -5. You can also phrase that as the maximum point is -5, comma, -3. Vertex form is pretty straightforward, or again, what our book calls standard form, pretty straightforward. So it's really nice to come up with the vertex if our function, or if our quadratic equation is in that standard form, or what I refer to as vertex form. But what if we have y is equal to a squared plus bx plus c? What if we have the general form? That's a little bit trickier. Now, I'm going to essentially right now give you where the vertex is at. And we'll see why this is the case a little bit later. Probably, maybe not today, but a little bit later. It turns out if we have this general form, y is equal to ax squared plus bx plus c, then the vertex is going to have an x value of opposite of b over 2a. And the axis of symmetry is going to be x is equal to opposite of b over 2a, excuse me. Now this tells me the x value of the vertex. How would I find the y value of the vertex? Well, once I know the x, just plug it in and get the y. Does that make sense? Now you could plug it in right here, like to this x and this x in general and get an expression for y. But usually what happens is that x will be equal to a number and just plug in that number. Okay, so usually what I do is I memorize that the x value of the vertex is opposite of b over 2a, and I don't remember the formula for the y value. I just say, well, now that I know the x, plug it in and get the y. But there is a formula for the y value, and you can figure it out by plugging this in and trying to simplify that expression. It's messy though, it's messy. So opposite of b over 2a. So let's take a couple of functions, a couple of quadratic equations, quadratic functions, and do the same thing we did earlier. We'll figure out which direction the parabola is pointing. We'll figure out where the vertex is at, axis of symmetry is at, and then min and max value. So here are our two equations that we're going to deal with in general form. Is this first one a parabola that's going to point up or down? Up. Why is that? Yeah, the coefficient of the coefficient of the x squared is called a. That's positive. So it's going to point up because the a is positive. Now I know I didn't mention this yet, but I just want to take a sort of sidebar. When we wrote our parabola in what we call standard form in the book, or vertex form is what I like to call it, I had an a in front. When I write my parabola in general form, I have also an a in front. These are the exact same a's. So we said this can easily be seen as a transformation of my base parabola. And we said that because of that, if A is positive, I know the parabola is pointing up. If A is negative, the parabola is pointing down. Well, since these two are the same A's, that means if this one is positive, it's pointing up, and if it's negative, pointing down. Everybody understand why they're the same A's? Essentially, if you multiply this thing out, what you would end up with is y equals ax squared minus 2 times a times h times x plus a h squared plus k. And so notice that the ax squared give me the same a, right? And by the way, this is also why the vertex of the parabola has x value of opposite b over 2a. Notice this is the coefficient of the x that's equal to b. So opposite of 2a times h is equal to b because of that multiplication out. If I solve for h by dividing negative 2a on both sides, I get that my h is the opposite of b over 2a. And we saw that if our parabola is in this form, h is the x value of the vertex. So the x value of the vertex is opposite of b over 2a if we're in this form. So that's why that opposite of b over 2a gives me the x value of the vertex. It's just because that's what we get when we expand this out. And that's also why these two are the same a's. And now I know that whenever that a lead coefficient of the x squared is positive, it points up. It's negative, it points down. So that was just kind of a sidebar on what the real goal is. The real goal was to assess this parabola. Okay. All right, so now we know that it points up. If we're trying to find the vertex, the x value of the vertex is going to be opposite of b. In this case, b is 6. Divided by 2 times a. A in this case is 1. That's the coefficient of the x squared. So we get that the vertex is going to have x value of -3. And the vertex is going to have y value of whatever I get when I plug in -3 into this. So I just plug in -3 in for x. I believe that's -19 when I calculate it. Try to do that in my head, but. So the vertex has x value of -3 because that's opposite of b over 2a, and then I find the y value just by plugging in -3 into my expression. Everybody okay that I use the f of x and the y interchangeably? We're all set with that. That should be fairly obvious. So the vertex, I know now, it's the point -3, -19. And that means the axis of symmetry is x is equal to -3. And that means since we're pointing up, I get an absolute minimum at that vertex. So minimum of minimum y value of -19 happening when x is equal to -3, or the minimum point of -3, -19. Why don't you go ahead and try the next one on your own? Do the same thing about where the parabola points. Then find the x value of the vertex. Use that to find the y value of the vertex. Write down what the actual vertex is. The axis of symmetry. And then minimum or maximum. And if you get a decimal or fraction, you can write the decimal, that's fine. Might be easier to write the decimal in this case than dealing with the fractions. All right, this can go, again, it usually goes fairly quickly. In this case, the B is 9 and the A is -3. So I get -9 divided by 2 times -3. The negatives will cancel out. We'll have essentially 9/6, which simplifies to 1.5 as a decimal or 3/2 as a fraction. So I'm going to use the decimal of 1.5. And then to find the corresponding y value, I just plug in 1.5 into the x. When I did that, I ended up with a 14.75 as the correct y value. So the vertex is happening at the point 1.5, comma 14.75. The axis of symmetry would be x is equal to 1.5. That's the vertical line, x equals 1.5. And then we'd say, because this parabola had a negative a, the parabola would be pointing down. And therefore, that vertex that I just found is going to be a maximum. The maximum y value is going to be 14.75, and that's going to happen when the x value is 1.5. Oh, there we go. By the way, if you ever wanted to check your answer, one way to check it is to actually just go ahead and graph, either on your graphing calculator or on Desmos or any other graphing device. So we can go into the y equals menu and graph. The one we first did was x squared plus 6x minus 10. And then we could, I'll do the standard graph that. Notice that if I use the standard window, my vertex is below there, so I'd have to adjust the window. The x values aren't too bad, but the y values I'd go down to maybe -25. And now we see the vertex, right? I think I showed you did I show you finding minimums? So you can trace, and then you can kind of like scroll around, and you can get to about your lowest point. You can plug in a number of -3 and see that you are at your lowest point. That's one option. If you wanted to confirm that that is your minimum value, one way to do it is to go into the calculate menu. Second, calculate, down to number 3. Gives you your minimum. And then it asks you for where you're looking for your minimum. So you go left bound, right bound. We're going to say our minimum we can visually see is somewhere in that interval. And then a guess, I'll guess here. Notice that the calculator gave me -2.9 repeating and then -19. just a calculation error. So that's actually just -3, -19. And if you choose a better interval or a better start value, you might get exactly -3, -19. So you can do that and confirm your vertex, confirm you get the parabola that you're looking for based on that. The other one was -3x squared plus 9x plus 8. If I zoom standard that one, well, now the vertex you can see is too high. So we change the window, put that up a little bit. Instead of changing the wide minimum, I have to move it up a little bit. Let's move it up to, I'll say 18, I guess. Kind of know what's going to happen. So there's your vertex. And if I wanted to find the vertex, since it's a maximum, I would just choose the number 4. Left bound, right bound, and then I'll do a guess. Guess is about right there. There you go. Again, because of rounding errors with your calculator, it doesn't give you the exact value you want, but you can see it would round. If you rounded to 2 decimal places, it'd give you the exact same value. So that's 1.5, comma 14.5. 14.75, excuse me. So 1.5, comma 14.75 as your vertex. So if you wanted to confirm your results, you can always just graph those and see how that works. See if they look right. And you could have also graphed it on Desmos too, if you had access to Desmos at the time. Now, the last concept I'm going to talk about for today is the concept of the x and y intercepts of a parabola. Remember that my domain is all real numbers for a quadratic function. So a quadratic function has domain that's all real numbers. So we're going to go forever to the left, forever to the right. At some point, we're going to cross that y-axis. Therefore, a quadratic function is going to always have one y-intercept. And it's going to happen when x is equal to 0, just like every other y-intercept. Because of the way a quadratic can look, quadratic function that is can look, it can either have 0, 1, or 2 x-intercepts. Okay. And if you want to find the x and y-intercepts, well, to find the y-intercept, we just plug in 0 for x. If we want to find the x-intercept, we plug in 0 for y. Plugging in 0 for x is really easy to do in a quadratic scenario. We just plug in 0, evaluate the right-hand side. Plugging in 0 for y means we're going to have to solve quadratic equations. Now, before I get to that, let me explain graphically why a quadratic function can have 0, 1, or 2 x-intercepts. Everybody see why it has to have 0, 1, or 2? Well, it's because of the nature of the shape of a quadratic function. it has this parabola shape. So notice that we could, like in this case, have a parabola pointing up with a k value of 3.5, and it never crosses the x-axis. So there's no place where the y value reaches down to 0. So this means you would have no x-intercepts. As you start moving that k value, you can get closer and closer to the x-axis. At some point, specifically with that k of 0, you're going to touch the x-axis at one point, which is your vertex. And so if my vertex is on the x-axis, that means I have one x-intercept. And if our k value goes below, let's say -3, then obviously we're having a parabola which crosses the x-axis at 2 points. So the shape of the parabola forces us to either have 0, 1, or 2 x-intercepts. Okay. That's the same case if we flip the parabola upside down. It could never come up to touch the x-axis. Having one x-intercept means that the x-intercept happens at the vertex, where the vertex touches the x-axis and nothing else does. Or in this case, if our parabola is pointing down, if the vertex is above the x-axis and parabola is pointing down, then we end up with 2 x-intercepts. Right? And our shift left and right isn't going to matter. It's not going to affect how many x-intercepts we have. It's going to affect where they're at, obviously, but not going to affect the number. So we're going to get 0, 1, or 2 x-intercepts. And we always have one y-intercept. The y-intercept happens when x is equal to 0. The x-intercept could happen when y is equal to 0. To find the y-intercept, we're going to have to plug in 0 for x and then evaluate. That's very nice. To find x-intercepts, we're going to have to solve quadratic equations. So imagine I have this quadratic equation. Y equals x squared minus 2x minus 5. In order to find the y-intercept, I need to plug in 0 for x. That's pretty easy to do, no matter what type of equation. If I have a general form like I do here, or if I have the standard form, which is the vertex form, I go 0 squared minus 2 times 0 minus 5. So the y-intercept is the point 0, -5. If I were to find the x-intercept, we would plug in 0 for y. And I'd have 0 equals x squared minus 2x minus 5. And I would need to solve that quadratic equation. By the way, notice this is a quadratic equation in variable x. We only have one variable, that variable is x. So we need to solve the quadratic equation for x, essentially. Once we get answers, then we can determine if we have x-intercepts, if we have 1, 2, or 0 x-intercepts. And there we go. Excuse me. So the question is, how do we solve quadratic equations? And that's the big thing that we're going to do next time. All right? Next class period, a lot of next class period, at least the beginning of next class period, will be focused on solving quadratic equations, meaning I have 0 equals to some quadratic x. And how do I solve these? So this is what we're going to do next time. And just as a preview, we're going to have different methods. We'll have factoring, we'll have the square root property, we'll have completing the square, we'll have the quadratic formula. Although, to be very blunt, completing the square and quadratic formula are kind of redundant. So generally speaking, I'll just use the quadratic formula. Okay. All right? So that's what we'll do next time. We'll start solving quadratic equations, and we're going to be doing that because it is linked to finding x-intercepts. All right? Of these quadratic functions. All right, other than that, I will see you all